On this channel, we provide useful programming information with practical code examples. This time, it's about the multiprocessing module in Python. This article introduces practical tips for writing safe and efficient parallel processing code using the multiprocessing module. Enabling subtitles will make the code descriptions easier to understand. Multiprocessing enables parallelization on a process basis, so you can parallelize CPU-bound tasks without being restricted by Python's GIL, Global Interpreter Lock. For I/O-bound tasks, threading, or async I/O, may be simpler and more suitable. First, here is a basic example of running a function in a separate process using process. This demonstrates how to start a process, wait for its completion, and pass arguments. This code shows the flow where the main process launches a child process, worker, and waits for its completion using join. You can pass arguments using args. Pool.map is useful when you want to apply the same function to multiple independent tasks. It manages worker processes internally for you. Pool can automatically control the number of workers, and map returns results in the original order. Queue is a first in first out FIFO queue that safely transfers objects between processes. Below are some typical patterns. Queue allows you to safely pass data between processes. It is common to use a special value such as none to signal termination. You can use value and array when you want to share small numbers or arrays between processes. You need to use locks to avoid conflicts. Value and array share data between processes using lower-level mechanisms, shared memory at the C language level, not Python itself. Therefore, it is suitable for quickly reading and writing small amounts of data, but it is not suitable for handling large amounts of data. If you want to use more flexible shared objects like lists or dictionaries, use manager. Manager is convenient for sharing dictionaries and lists, but every access sends data between processes and requires pickle conversion. Therefore, frequently updating large amounts of data will slow down processing. Use lock or semaphore to control concurrent access to shared resources. You can use them concisely with the with statement. Locks prevent data races, but if the locked region is too large, parallel processing performance will decrease. Only the necessary parts should be protected as a critical section. On Unix systems, processes are duplicated using fork by default, making copy on write for memory efficient. Windows starts processes using spawn, which re-imports modules, so you need to take care with entry point protection and global initialization. Set start method can only be called once at the start of your program. It's safer not to change this arbitrarily within libraries. Below is a script that simply compares how much faster processing can be with parallelization using multiprocessing. Here, we use pool. This example shows that depending on task load and the number of processes, parallelization can sometimes be ineffective due to overhead. The larger, heavier, and more independent the tasks, the greater the benefit. Below are the basic points for using multiprocessing safely and efficiently. On Windows, modules are re-imported when child processes start, so you must protect your script's entry point with if name equals main. Interprocess communication is serialized with pickle conversion, so transferring large objects becomes costly. Since multiprocessing creates processes, it's common to decide the number of processes based on multiprocessing.cpu_count. Creating another pool within a worker becomes complex, so you should avoid nesting pool instances as much as possible. Since exceptions occurring in child processes are hard to detect from the main process, it is necessary to explicitly implement logging and error handling. Set the number of processes according to the CPU, and consider using threads for I/O-bound tasks. Below are some useful concepts and patterns for designing parallel processing. It is efficient to separate processes into roles such as input reading, I/O, preprocessing, multi-CPU, and aggregation, serial, via pipelining. To simplify debugging, first check the operation in a single process before parallelizing. For logging, separate log outputs per process, e.g., include the PID in file names to make isolating issues easier. Prepare retry and timeout mechanisms so you can safely recover even if a process hangs. Parallel processing is powerful, but it's important to correctly judge the nature of tasks, data size, and interprocess communication cost. Multiprocessing is effective for CPU-bound processing, but poor design or synchronization mistakes can reduce performance. If you follow the basic rules and patterns, you can build safe and efficient parallel programs. The source code for this video can be downloaded from the official website. If you like, please visit the URL in the description to aid your learning. Thank you for watching. If you'd like to enjoy more content, please subscribe to the channel.